Okay, let's see if I can make this all work nice and pretty. I need more screen real estate. Anyone run out of screen real estate?
Yes.
Totally, right? You understand why web developers have more screens than anyone else, even though they're not doing stuff. I can open up Unity on a big screen and go maximize, and all of a sudden, you've got everything you need in front of you. And when you work on the web stuff, you guys get now why I don't maximize things and why I have little windows all over the place? Because eventually you've got like 6 things open. Where did that debugger go? This stuff's all leading up to building an actual game. And to build our games, in the short amount of time we have left, we are going to do a couple things that will probably cause you a little bit of grief to begin with, but they're good parts of learning. So the first thing we're going to do is we're going to take a look at exactly how do games fit together, because games are really just this. They're real-time simulations. We're going to simulate something. We're going to change some conditions. We're going to update some model. And then we're going to interrogate it and draw its current state on the screen for everybody to see. At which point we're going to collect some more inputs, update the model, redraw the scene, and do that over and over again. And this is exactly what modern game engines are doing, and in fact 99% of the time they're hiding it from you. If you were to ask somebody who hasn't done a lot of programming work, how does Unity draw the screen? They're probably kind of lost at where that begins, or where does execution begin in Unreal. And hopefully by going through some of this, we're going to expose some of that to you in a little bit gentler way than having to dive into C++ and draw a rendering engine from first principles where you have to dissect triangles and open a graphics context and start transforming stuff with a little bit of matrix math, because that would be really hard, right? It used to be the entrance criteria for one of the senior programmers I had work for me. If you couldn't fly a camera through a 3D scene written entirely by yourself in C++, they wouldn't even give you an interview. Showed that as a demo, right? So we kind of want to get past that step. There's a couple other things that come with this. You got basically 4 weeks, and that means, one, you're going to need some levels to display. Good thing you built a level editor, because you're probably going to be messing around with that level editor to generate test data faster. The other thing is you will very quickly find that your level editor is not 100% there. In other words, there are going to be things you're going to discover as you're building your application or your game with whatever theme you choose that you're missing from your level editor. And it's totally cool to go back to the level editor and update them. Add the things you need. In fact, it might be a whole lot easier to add a new system, to add new kinds of objects into your level editor than it would be to manually go into the level data files and manually edit or change them. Right? If you can imagine pushing things around a few pixels a little bit, you build some things that you stack up, and when you stack them up and run them in the game, the physics has them all topple over. I need to push the legs out a little bit. Okay, well, how many pixels is that? Do I have to go into a JSON file and edit it? That's a pain in the... I'll just open that up in my level editor and modify it. So in order to get all of that stuff in, we're going to work in pairs. So we're going to put together groups of 2 to build the game. And there are a couple major parts to this game that have to be constructed. First of all, there's a very big user interface component, all the view stuff, all the stuff you draw on the screen, all the user interactions. Because it's a game, you have to have some controls. You probably should have a splash screen explaining the controls with a little play button that hides itself. And then you go into the game where you have to pick a level, so there's a pop-up dialog, right? Or some drop-down menu of some kind. You load that level from the exact same code that you used in your level editor to save it and load it. So you want to be able to reuse stuff you've already written. You don't want to have to rewrite that again. Once you load it, life's going to get interesting because you need to attach some additional information and objects attached to that level data. So trying to do this non-object oriented is going to fall flat in its face. There's just too much complexity, and you need to work with the different components that we're building. Okay? Now, you don't need to build it exactly the way I build it. There are lots of different opportunities. The other thing is, I'm going to give you some parts to it that are going to make your life easier. The biggest part I'm going to give you is the part that does a lot of this for you. It's the physics library. Now, the physics library requires you to think about and do things a certain way. And that's going to create a little bit of grief. On the other hand, it does all the heavy math for you. So we're going to talk a bit today about what that library does and how it does for you. Okay? We're going to fit those pieces together. The other thing we need is we need a real main game loop. We're going to have to build that ourselves as well. We don't have a framework or an engine we're working with, so we're going to have to build that. Now, fortunately, it's not complicated. The principle is really straightforward. There's some idiosyncrasies we'll deal with in JavaScript. It has some really nice ways to do it. Okay. What I do recommend, although there are solutions out there that use HTML canvas to draw stuff on the screen, I do not recommend using them. Okay. And it's not that they're bad, because we're going to get into playing with canvas at some point. But it pushes everything into JavaScript, and it pushes a lot of extra math into JavaScript. And by doing the stuff with the DOM, by creating divs with images on them, we can reduce our problem down to manipulating a bunch of boxes. And we can manipulate those boxes more easily using the DOM than we can with an HTML canvas. So it's not that it can't be done, it's just a little bit less work as you go. So there's two sides to this application. Okay? One, the real-time simulation side. That is loading a level and attaching all of the real-time modeling elements to it, so that when you start simulating your game environment using a real physics engine, all of the update sides of things happen nicely. There's another half to this, which is how to draw it all. Rendering everything on the screen in the right locations, and then handling all the user inputs, all the event handlers and all the jQuery DOM manipulation stuff. And what I recommend when we put teams together is sit down and divvy up the work between those two kind of layers. Okay? And particularly if you really found that the communication, Ajax, talking to the server stuff kind of clicked in place and you kind of got a good sense of that, then volunteer to do the user interface stuff. Okay, do the thing you're not comfortable with. I know, it sounds weird, right? And then likewise, if you found that dealing with manipulating divs and CSS and stuff kind of comes natural, but dealing with the asynchronous stuff is hurting your brain, I would say go back to working with that stuff. I often refer to the Ajax side of software development using asynchronous communication is kind of like a gateway drug. Once you get it and you understand it, you're well on your way to being a full stack developer instead of just a front end developer. And B, you open up a world of APIs, of third party tools and capabilities that most people don't even think are possible. Right? Stuff like Google's Vision API, stuff like machine learning, are all accessed through these third-party APIs, and they all work in the exact same way you just did. So once you get the way that works, you're opening up a whole slew of new capabilities to you. So what are we going to have to deal with? Well, the first thing we're going to have to deal with is timers, intervals, handling user events. We've got to build a main game loop in the next application. And the main game loop kind of always follows the same basic principles. It's always a while forever loop, or while the game's not finished. And the reason we do that is that in every kind of game except a PC game, you can't exit. There is no way out. When you boot a game on your console, that game starts, and the only way to get out of it is to go into the console's operating system and literally reboot it or soft boot it. That's the way the consoles flip in and out. Okay? It enables the application that's running to access the entire console memory. That's a good thing. Okay? It also means that it cleans up behind itself when it's done, so there's no memory leaks. Now, when we get to PC games, we can often get out. And that's an exit condition. And all that is making that main event loop have a while not done loop instead of while forever. Okay? And the way I suggest we kind of hook this stuff up, and this has actually changed a little bit. I was looking just the other day at the way jQuery does this. So jQuery had a ready method. And the ready method says, wait till all the HTML, CSS, and JavaScript is loaded before you start running. It just slowed things down a little bit. And it had some great value where you had a really complex application starting. And the thing it was giving you was you weren't about to start running some JavaScript that would access some part of the document before the document was loaded. Your browser's doing a whole bunch of asynchronous things in the background, right? If you've got 5 CSS files you're loading and a jQuery library, it'll make 5 asynchronous calls out to 5 different locations. And they're going to come back at different times. And so if you try and execute some stuff before everything's loaded, you could get it to the point where it says it doesn't work, you get a white screen, nothing shows up on the screen, you open it up in the inspector, all the HTML and all the JavaScript is exactly the way you expect it. And that's kind of a problem. So we would often bake our applications into a little main program that just said, hey, wait till everything's loaded, and then start our application by creating a new game. And then telling that game to start running itself. Okay? And that's the basic framework we're going to use. We're going to wrap this a little bit differently. Right? We'll probably put this in a DOM content loaded handler. So we'll just listen until all of the DOM content is loaded. We really want the HTML, CSS stuff, right? And then we'll do this kind of. Now, what does that main loop look like? Well, here's one possible way to do it. If you're not familiar with it, the document has a couple interesting side effects or interesting things attached to it. Like any library, they don't document everything all in one spot. The browser loads the document. The document is an object. The document actually has a parent, and that parent is called window. And if you've ever not used one of those fat arrow functions I told you to use, but used a real function like the jQuery documents do, you'll find that this reference, this dot something, is pointing at the window when you try and have an event that you get triggered. And that's kind of problematic because I really want it to point to the object that's handling the thing. So that window object has a bunch of extra capabilities attached to it. One of the capabilities it has attached to it is timers. And it has a timer that you can either do set timer or set interval. Now the reason I bring up that window is that in this example, to fit on a slide, I've dropped the window dot part of this. This is really window dot set interval. Okay? And the way set interval and set timer work is they take a function as a callback and a time in milliseconds to wait before calling that call again. You don't want to do anything recursive in there, but really, if I want to run at 60 frames a second, what I do is I figure out what 60 frames a second is, Okay, so I take a second, that's 1,000 milliseconds, and divide by 60. And what number do I get? Because as game devs, you memorize this. It's 1,000 divided by 60. What's 100 divided by 6? It's the same thing. Right? How long do you get?
0.016.
0.016, or 16 milliseconds. Right? Plus some change. So the magic number to stick in your head is 16 milliseconds. That means if you want to run at 60 frames a second, every time we think about the way our game runs, the only thing we're concerned with is what happens in one frame. What happens in one frame? Well, I'm going to update everything, do whatever AI, math, physics, everything. I'm going to update it. Everything kind of in world position, world coordinates. And then I'm going to go render it all. I'm going to go draw it all again. Right? And the render thing is going to need to interrogate the model to figure out what to draw. Where are you now, kind of thing. Okay? And then we're going to wait. Okay? Now, as we start to wait, what happens if we take longer than 16 milliseconds?
It'll start doing this again.
Right. So if I'm looking at, I'm going to see if my magic works today. If I'm looking at something like this, and I'm checking out the timing here, and I've got 16 millisecond chunks, okay? If I start doing some work and I don't finish before it's time to draw the next frame, the next one just starts. Okay? As soon as I'm finished, I draw it. As soon as I'm finished, I draw it. And the next one doesn't start till here. Okay? Now we run into a problem if we get to a place where we start them and they're finishing, and it takes more than 16 milliseconds. Because sooner or later, this gap here is going to get bigger and bigger. Right? They're always going to start at the 16 millisecond boundary, but because this is taking longer, and JavaScript single-threaded, this can't really start operating till here. So it's going to take a little longer, a little longer, a little longer. So you see this in two ways. One, when you do this kind of hard-coded render loop, two things are going to happen. Either you are going to measure and optimize these so that they happen in under 16 milliseconds all the time, in which case you're fine. Everything runs super smooth. If you don't do that, if either one of these takes too long, then eventually what will happen is you'll have so many of these set intervals stacked up that haven't completed that you'll exceed our stack, literally. Because every time we call set interval, we got to put a whole function and a time on the stack again to be called later, because that's why they're called callbacks, right? So it takes all of this code as text and it puts it on the stack. Here's the script to run. Again and again and again and again. Now at the speed our computers run, you will run out of stack space for the browser very quickly. Even with 32 gig RAM, you're probably talking about a few seconds. And the net result is your browser will lock up. And the only thing you can do is go to the task manager and kill the browser at that point. Okay? It's no different than going into a C++ application and allocating memory until the machine dies. Right? The machine will let you allocate memory in a C++ application far beyond 32 gig. It'll just consume the disk until all the page swap space in the disk is gone. And then it'll do one more allocation, and that allocation will fail. And if you don't handle that failure, it'll just sit there without the operating system being able to do anything about it. That whole process will have to get killed. So in principle, this is what we're doing. In practice, we're going to do something different. Once people started doing a little bit of this, the next thing they started thinking about was, well, how do I stop it then before it becomes a problem? This timer object, this is something the operating system or the browser hands back to us, so we can hang on to that timer. Now I've attached it to the object that this run method or the game object is inside, so that I can stop it. So they kindly provide us with the clear interval. And now I can do something a little smart. During the update, right, I'm going to hang on to the timer. I'm going to set my interval. During the update, I'm going to go check the user to see if they did anything. And if they did something like press the exit button, I'm going to set a flag, the game over flag maybe. So if the game is over, then I'm going to clear that interval, and that's going to stop the timer from running. Okay? So now we have a way that we can get this thing looping, and we can get a user to stop it. And this is not entirely the way games run. This is closer to it. Okay? As this interval timer became a real problem to kind of like manage that 16 millisecond time, and HTML5 came out, and HTML5 added a bunch of capabilities to the browser. It said, hey, you know, it's 2010, and browsers can do more than just show some simple text. So let's turn around and let's see if we can add some capabilities. So they updated HTML with HTML5, and the big thing that was really added was a canvas, which was the ability to access the drawing canvas in the browser directly for graphics. Great, cool. There's a bunch of other things that came with it. As soon as we could access the drawing canvas, we needed a way to be able to know when we'd finished drawing something. And that thing they added to the window object was the request animation frame method. And the request animation frame method behaves a little differently. What it does is it's a recursive method that says, here's what I want to do, and I'm not going to do the next one till I finish the first one. Okay? Now, by doing this, we don't have to, as programmers, make sure that that update render part stays under 16 milliseconds. And we're not ever going to blow through the stack, because we're only going to have one outstanding request, one outstanding function call. The other thing we have, though, is now we have what we call floating frame rate, which is the way all our modern game engines work. Okay. Now, the challenge with a floating frame rate is when I go to do this update, I don't necessarily know how much time has elapsed since the last time I updated things. If I'm only running at 20 frames a second, I might have had a lot of time, like 30 milliseconds have gone by. How do I compensate for that? Well, we compensate for that by passing in the amount of milliseconds that have passed since the last time one of these things was done. And it's up to you as a developer if you want to use that delta time to change the way you compute or calculate things. So you can hard code it and you only get like 16 milliseconds of update every time. Or you can let the frame rate completely float. And you can update your physics and your AI and the positions of all your enemies in the world as fast as the delta time lets you. And then on the render side, you probably want to know that as well, because you're going to have to redraw things. And if they've moved too far, you're going to have to like draw the screen blank first and then draw it in the new position. Unless you're in the web and you use the DOM, because we could just translate things around. Okay. So we're going to use this to do our run method. And our run method's not going to be that different from this one specifically. Okay. It doesn't really need to be. This delta time, I'm going to keep track of the start time as soon as I start the run method. And I'm going to update it, kind of like this. And I'm going to figure out how much time I've elapsed when I'm first developing it, the guts of these two guys are gonna kind of ignore it, because it's a nice subtlety, and as long as we're running over 60 frames a second, we're good. The request animation frame is gonna make sure that we don't blow through the stack. So it's just gonna throttle itself. So if you do something dumb, your whole thing's not gonna die. You can stop it in the debugger. You can debug what you did that's not working properly. It'll just go slower. And that's gonna be a big benefit to us figuring out how we build this application, okay? Now, what do we do in the update and render methods? Those are part of the game. So I'm a lazy programmer, so I'm gonna push and defer it all off onto other things. Okay. The first thing is, all I'm going to do in the update is tell the world to update itself. In fact, everything I build is probably going to have an update and a render method. Okay. Now, in terms of how are we structuring our application, I'd be a little bit remiss if I didn't kind of illustrate it this way. Our application.
Oh, the Nick is not gonna see this. Nick is not gonna see it.
Yeah, he is. I'm cheating. I'll show you something special. I have a second camera running.
That's right.
Yeah. I'm one step ahead. It's a little far away. But basically, if I draw big, it'll work. We got this view thing that we're working on, right? That's what you see. That's the HTML and CSS part. That's the document itself. So the browser handles this for me. All I have to do is manipulate it or update it. And then down here, I've got some model. Okay? That's going to simulate what's going on in the world. And this is going to be our physics engine. So we're going to set up our physics engine with all the blocks and things in our world, targets, cannonballs, everything. And we're going to say, hey, we're going to access that through some controllers. That's what you write. So if you do this right, the document object managed by the browser, you can use the controller to manipulate it, to collect inputs from the user, take those inputs from the user, update the model. The model does something, right? And then the controllers interrogate the model and update the view. We're going to need some organization to help us with that. Okay? This is the first one. If in here, I'm not going to use red because it'll never show up, but if in here I were to build an object called the world, short for the world controller, the world could keep a reference to the model and a reference to, say, a jQuery object that's its view. Like the whole gameplay area is the world. So when I tell the model to update itself, it tells the physics thing to do its thing. And then when I tell the world to render itself, it goes and interrogates the model and updates all the CSS. This thing's now here. This thing's here. This
But
thing's
the model gets like, oh, this cannonball is not in position X and Y in this position, and that's
So what does this do? Okay. This needs a representation of what's going on in your world. And from that representation, we are going to apply forces. Physics, right? And forces really come in two flavors. Those forces are either impulses or forces. Okay? And the best way to think about them mentally is that a force is like someone attaches a rope to your center and pulls on you continuously. The other way we can think about them is an impulse. That is, someone walks up behind you with a baseball bat and gives you a crack in the middle of the back. Okay? In both cases, you're going to move in the same direction. With a force, it's constant, it's continuous. You will continue to be pulled in that direction until someone lets go of the rope. With an impulse, that baseball bat, you're going to get knocked forward quite abruptly initially, but it's going to fade over time. Okay? Now relate this to the Angry Pigs demo I showed you earlier. The number one force that's applying on all the things in that world, what would that force be called? Gravity. It's just a force like anything else. I made gravity point down. So everything has gravity pulling on it the whole time. When I shot a pig, I applied a big impulse to the pig. The vector I applied that impulse along was directly taken from the angle of the cannon. The angle of the cannon gave me the angle to put the impulse on. Once I put that impulse on, that pig also is affected by gravity. What the model part does, what the physics engine does, is it manages those forces. It manages all of those entities we create, which we call rigid bodies. And all of those rigid bodies, sooner or later, do fun stuff. They collide with each other. And I don't want to do the crazy math, because when two things collide with each other, I've got to take all the forces involved with all of those things and compute new forces for all of them based on the angles and the size of the forces, right? I also have to take into account the size of the objects, the mass of the objects, how much restitution they have. In other words, how bouncy or not bouncy they are. And also how much friction is between them.
Restitution is bounciness?
Yeah. Bounciness, restitution, same thing. Restitution's the physics term, and bounciness is the easier way to think of it, right? From 0 to 100%, or you put a 0 to 1 value there. Same with friction.
Oh, because in the level editor I can put 900.
As long as it gets clamped down to 1 when you get back into the game, that's fine.
No, I can
Yeah. Let me change that right here, right now. You can give people a spinner and make it 100%. Turn the 100% into a value. That works. Okay. Now, when two things collide, that's a certain amount of math that's kind of painful to do, right? And let's see. That's not the one. This is all done with the same physics library we're going to use. So it can handle lots of stuff bouncing around. Now, I'm probably just like you at this point. I don't want to do the math. Every time this collides with this, I got to figure out new force and impulse vectors for every one of those things. And when I do so, the collisions might cause them to bounce. And when they bounce, they're going to hit the next thing beside them, and the next thing, and the next thing. So this is what the physics library does for us. It says if we set up the model right, it'll do all the math. We just have to tell it how long to simulate. Like 16 milliseconds. Can you simulate 16 milliseconds for me? And then just tell me where everything is. Then we go interrogate that. We update all the CSS, and we do it again. And at 16 milliseconds, it's fast enough that we get nice, smooth animation in the world. So that's kind of what we're shooting for. We're going to tell our world to update itself. It's going to do all the physics calculations for us, and then we're going to go interrogate it. Okay? Now, at first, this will sound relatively straightforward. Until we get into, like, how do we actually do it? So, every time we create something that we add to our world, we also need to add it to the model. In addition, instead of trying to walk through the model and the physics libraries API to find every entity, every game object, right? I'm going to call them a game object. Instead of having to walk through the world to try and find them all, I'm also going to keep a list of them. And I'm going to make my own list out of all of the, for lack of a better term, game object controllers. So that's where I'm coming over here and saying, well, I'm also going to have game objects. And I'm going to have a list of them. It's going to get really messy soon. Okay? That way, when it comes time to re-render them, I can just walk through the list of them, ask each of them where they currently are, and then call the controller's render method. So instead of me having to manage crazy lists in my game itself, here's the world, here's all the things I loaded from my level editor. Each thing I load from the level editor, we need to wrap a game object around that knows how to update and render itself. And part of the rendering is, how do I interrogate my model? And how do I update my CSS? Okay. Now the tricks for doing this with the DOM's pretty straightforward. CSS provides a very nice transform. Right? The transform style we can update with JavaScript very easily. And all we need to do is figure out where its new XY is and where its current rotation is. And then we can do some math and figure out, hey, this is where this object is and what orientation it's in. And if we do that for all the game objects, we've got the rendering part of it covered. So the world handles the update, and the game objects handle their own rendering. Make sense? Right. So that gets us to how are we going to put this all together. You've probably heard of it before. The engine we're going to use, the physics engine, is called Box2D. It's been around forever. It was originally written in Java. It's been ported to many, many libraries. It's kind of the basis of most 2D physics engines and libraries. It's not what we use in Unity and Unreal. They typically use an engine called Havoc that does this all in 3D. 3D makes things a little bit more complicated and a lot more beneficial to use a third-party library. Unity has distilled this down to the point where you can literally add a component to a game object that's a rigid body component and does all the same things that we're going to do. Okay? The library will provide a lot of these things for you. There's a few idiosyncrasies with it because it's kind of old. And so I've wrapped the library in a physics object for you and had a whole bunch of static methods attached to it. So all the things we're going to use, you can just go physics dot whatever. The advantage of that is if you ever want to swap out Box2D for another library, you only have to go to that one physics object I give you and replace the Box2D calls in there with the appropriate thing from the other library you want to use, which is one of those common kind of why do we build software in layers and build APIs between things. All right. Which gets us to the next part, which is we got to build teams. So I'm going to give you some guidelines, but I'm going to let you guys build the teams, or at least sort of. Okay? So the usual caveats I give you before I give you the rules are, think about who you would like to work with in the room. Okay? There's only 6 of you, so there's only going to be 3 teams. Over the course of the year, you're going to end up working with everybody on team projects. There's probably somebody in the room that you may not want to work with, maybe. And we don't really want to like just blurt that stuff out right away. So what we usually have you do is have everybody take a sticky note and write down 3 names. Okay, 4 really. 1, what do you put at the top of it? Your name. Okay. Second, list 2 people you would like to work with. You know, if I can't get my first choice, here's my second choice. And the third name you're going to write down is someone you probably would prefer not to work with on this project. Okay? You're going to fold it up. I don't see it. No one else in the class sees it. Only David sees it. You give them to David. David will build the usual little matrix we use. Okay? When it comes to figuring out who you want to put on that list of who you want to work with, the best advice I can give you is don't pick the people that you're the most friendly with. Okay? Instead, pick the people with the same work ethic as you. It doesn't matter about good or bad, because we're all learning. Okay? And there's all of us have things we know how to do and things we don't know how to do. Right? Certainly you can stump me on lots of Unity and Unreal questions. Yeah.
Shadro and Nick can be in the same team. That's cheating.
You can just do it the way I'm suggesting. What I suggest is you pick the work ethic. In other words, who's here normally hours when you're here and the number of hours you're here and working.
There's nobody like me. I'm here.
I know. We know you're unique.
Yeah,
We
you
really
know,
do.
You live here.
In some cases, that's a good thing, and in some cases, it's not. But we know you're unique.
You're special.
Yeah, actually.
We have all sorts of
special.
specials.
Scott, RC developed a sorting method called RSend sort into that data structure. Right, RC?
I don't think he actually implemented it.
Yeah, just yeah.
But he tried.
Nick, if you can hear us, Nick, you can message David with a PM. Don't put it in the channel. Kind of defeats the purpose.
Why don't you all message me?
My point is, if you're a morning person, don't pick somebody who's a nighttime person. If you work 16 hours a day on stuff, and someone else gets this stuff in 6 hours a day, you're not going to make a good team. Okay? And the reasoning for that is, if I'm working my ass off 10 hours a day, and David's not doing anything other than playing with his 3D printer for most of the day. You knew I was going there, right?
My 3D printer?
Yeah.
Awesome.
What's going to happen is one of us is going to feel like we're doing all the work. And that's not what we want. Okay? So if, and we've had this before many times, if you're someone who's here 12 hours a day or more, and someone else is here the same kind of block of time, you know, from noon till midnight every day, then you will make a good team, because you can always get a hold of each other, and you can always like yell across the room like, can you build me something that does, can you add this parameter to this thing so I can get it? Can you add this to me? What do you need to be able to do the thing you're doing, right? And if you're not here at the same time, if that communication is hard, then this will be hard. The other thing is we're going to set up the Git repos for you. Because obviously you're going to have to share code, which means you're going to have to use Git. And using Git does not, like constituting using a source control system, isn't I write it all on my machine and hope the hard drive doesn't fail. And then at the very end, I take the whole thing at once and make one commit, okay? there's very bad managers out there. We want you to make sure that they think you're a stellar developer too. And bad managers meaning they count semicolons in code, and they look at the number of commits in the source control system.
To see if you are working.
Yeah.
Oh, that seems.
Yeah.
Yeah.
If I have 72 people
Mhm.
working on a team, 35 of them are doing 80% of the commits. My boss comes to me and says, you got to get the 72 down to 60 people in a week. You got to fire some people. Who do you fire? Well, who's contributing the least? The people who aren't committing anything. So that's an easy choice, right? You just look through the source control system and go, once a week, 72 times a week, you two are gone.
Yeah, our commits are impeccable. Like we're working on it like 10 hours and making it perfect and then committing, and they're just doing random stuff.
You're better to have 1,000 small commits than one big one. Because the ultimate reason we're doing those commits is so that I can roll back out of it. So if I've got 100 files in one commit, rolling back out of it, I probably roll back more than one feature. Usually it's one feature, one commit. Right? One bug, one commit. And if that bug has got 3 files, that's fine. Or 10 files. And the source control systems can handle tens of thousands of commits per day, per person. So if you're getting a few hundred, I mean, I'll show you what it looks like.
I only have 11 for this project.
I only have 0.
This is a bad manager thing. Like, don't get me wrong.
No,
Like,
I'm not
good
saying
managers
I'm doing
don't
for
do
that.
this stuff.
But I think it should commit more of this. When they got things done.
Ugh.
You should. Especially if you're working here in your home computer. Especially for that
Yeah,
reason. But
yeah.
Not comfortable with the social media.
the hard part is resolving like search problems. Though.
The information's in front of you. So if we look at, say, project dev, the team's on the floor. Once GitHub logs me in.
Oh no. I forgot to create my project into VFS again.
So here's one of the projects on the floor, and their source code and their main branch and their develop branch.
How many people are usually on a team in these final projects?
Final projects will be between 4 and 6 people. Okay. And with you guys, I would assume that only there won't be multiple of you on the same team. In other words, I assume you guys will be split up into 6 separate teams.
Just like the Term 3 small project.
Yeah, the Term 3 small project is a microcosm of these projects.
The
It's
final one-
7 weeks worth of work, and the final project's 14. And hopefully you learn enough in the 7 weeks
So I can-
that you don't repeat those mistakes in the 14 weeks.
Yeah, I expect
Right?
that.
But if you click on Insights here, now one of the things we tell people in the final projects is if Quinn or I show up in the top 3 of contributions, you're in trouble. We're not. We're in the bottom.
Yeah.
Okay. That's good, right? And especially Quinn's is at the beginning where he set the repo up, put the template in there, right? And these guys look pretty good. And you can also look at total traffic, total commits,
That's a lot of commits.
okay? And over the last week, 104 commits on Wednesday. 5 people, 104 commits. That means people are doing 20 a day at least,
That's-
right? One bug, one commit. One feature, one commit. Oftentimes you'll have features that'll have multiple commits. I think I got it. Nope. I think I got it. Nope. I think I got it. Nope. Right? But if you try and put 10 features in the same commit, you can't get back out of it easily. And that's part of the idea is by using a source control system, I'll go down blind paths on things. I'll fork a branch and I will start working on something, and if I paint myself in a corner, I don't have to remember where was I or what was the last one that worked. I go back to the source control system where I forked that branch off and I'm like, just take me back to here. That branch I'm just going to abandon because it was junk and it didn't work out. Yeah.
One question. For 33, do you recommend create one branch for each one of us? Like I have 4 people in my team.
No, you don't do it on a per person basis, just like you never name something after a person or name a branch after a person. Name them by features.
Okay.
Because oftentimes you'll get multiple people working on the same feature. Right? Like if you have art and code, not always going to be the same person, right?
Yeah.
But it might be the same feature,
Yeah, it can be.
right? So it makes more sense to do that. We're going to get in depth more in this as we go, but for this project, this is a good first place to get where you've got 2 people you got to coordinate, right? Throw your stuff in GitHub, make commits to GitHub, right? And when your partner picks it up, they just get into this work habit. And the work habit is pretty standard in most companies. You get in the morning, you go to the source control system, you pull the latest stuff from the central repository, and you go get your coffee. Sometimes it's big. And then you sit down at your desk and you figure out all the things that broke when you pulled someone else's code and it merged into your own, because it's all on your machine. And you fix all those things and you commit the fixes back. And then you start working on your feature for the day. And as you finish your feature, you get to major working milestones. You make those commits as well. And hopefully by the end of the day, you don't have anything sitting on your machine, right, that wasn't strictly part of the project. I wonder if, do another one. Yeah, this is a good place to stop. So let's stop and take a break here while you guys figure out my little list of who to work with and who not to work with. Okay? Find a scrap of paper, find post-it notes. Do we have post?
All message me privately on Discord, it'll be easier.
Okay.
Like if Nick's gonna message me, then you guys all message me privately.
Yeah, that works. Okay?
2 persons working, but 1 not working. That's it?
Your name, well, that'll come through in Discord nicely. And then, yeah, 2 people, your first, second choice of who you want to work with. And then if there's somebody you don't want to work with, label them. Right? No one will see it.
Except for Dave.
Except for
Lots of
David.
people.
But my name's always on his do not work with list.
Really?
Because I just harass him all the time and he does all the hard work and I get all the credit. So he doesn't like that much.
Stay up with copyrights.
Right? He got to do fun things like assemble all the posts for the monitors in the other rooms and assemble chairs and, you know, make the 3D printer work again.
Or someone broke it.
Well, someone broke it, so you had to fix it, right?
Just happened to be with me as well, but you know.
So 15 minutes, 10 minutes?
Yeah, let's go 15-minute break.
Okay, sure.
So
Let's
you have
try-
time to do
yeah,
it.
Let's try to find
let's go back here and just before we set up the actual repository. So David and I will set up brand new repositories, okay? Once you get your team, you're gonna have to decide by playing with them whose level editor you're going to base on, right? And I recommend you look more at the internals than the user interface, okay? But if you want to look at kind of like typical commits,
Should it not be this thing? Should it be done in?
I can go you through if you want and give you the what is source tree doing. This is from March 21st. Okay? So in the last week, that's been my set of commits. In multiple different branches, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Oh, there's some things on this local machine I haven't grabbed yet. All right, a couple more minutes. I'm going to set up the repos here.
No, Scott.
Yep.
So the final assignment is going to be due week 8, right?
Pardon me?
No, the final assignment is going to be for week 8, right?
Yeah.
Okay.
Yeah.
Wednesday of vacation.
Yeah.
That's the final day anyways.
Yeah.
It's never getting full.
You really have to look at. All right. So let me sort this out, and then we'll get talking about some other stuff.
One more thing. Would say the harder part now or the building the game was harder for you?
So you made a bunch of posts. They were like secret.
No, it depends on how
Keep running.
I don't think one's harder or easier. They're very different.
Okay, got it. So maybe it's fine.
You shouldn't need to build anything new for the server
Make some posts.
to build the game.
Oh, yeah, so
We'll
make the
put
server
up
part.
make the new server as well. So let's pick your server. Thank you. So because you're gonna have to use the debugger for the server as well. The breakpoint in there as well. Hit the function that you're closing this one, so you get a note. There. Somewhere in there, the breakpoint.
All right. You all got your stuff to David?
Yeah.
Team stuff? Right? You got all your team stuff to David? Who are you going to work with?
Yes.
Yes? You've sent it to David. Okay. Okay. All right. So while David's figuring out the teams, okay, then we can start looking at how exactly are we going to put this thing together. Once we figure out the teams, I'll get your teams to create a name for your project. Okay. And we'll make the repositories because there's only 3 of them per project. So, how are we going to make this game?
It just crashed.
So here's how we're going to make this game. We're going to use this Box2D physics library to build the model part down here. Okay. And what that means is that game logic wise, when the user chooses a level, you're going to make a request to the server to go get the level data, right? And as you read the level data, not just building divs, but you're also going to have to build the physics entities that go with. Now, Box2D separates out everything into its own internal model. And it has a bunch of terminology, so you might as well get them kind of straight. The first thing is Box2D has a world object. And that world object is the container for everything. When you create that world object, you will specify a gravity vector. Right? Now, if you specify a gravity vector of 0, 0, 0, you're in outer space and everything floats. It just sits there, which can be kind of cool because, you know, when something hits, it still moves. It's just there's no gravity affecting it. You will build things called rigid bodies. Rigid bodies are generally represented as a single point in space. They have a couple properties to them. Specifically, they have a density, not a mass. Mass is computed. Okay? This is fairly dense in a small package. If I were to use the same density of liquid in something the size of this table, I couldn't lift it. Its mass is heavier, but density would be the same. So, when we build rigid bodies with Box2D, we're going to give it a density property. We're also going to build in Box2D a shape. And they have some predefined shapes that I highly recommend you use. In addition to those, you can specify a polygon shape. Remember, this is all 2D. Shapes help us determine the mass. You combine a rigid body and a shape. The shape tells you how big the thing is, right? The predefined shapes, not too surprisingly, circles, triangles, and squares or rectangles. I think divs are usually rectangles, so if you use a rectangle and a div, they kind of line up nice. Now, fixtures are Box2D's way of connecting the two things together. And part of the reason they do this is so they can reuse shapes, and part of the reason they do this is because some of the properties of how rigid bodies interact are in those fixtures. Things like the restitution and the friction. And once you start getting more complicated, you can add into your rigid bodies joints, right, and springs. And you can combine them and mix them in a bunch of different ways. We don't need any of the joints or springs for our game. Okay, so we just want rigid bodies flying around the world. Joints let you take 2 rigid bodies and connect them together and specify how they are articulated with each other. So there's lots of really cool demos. Just remember that this is a really old library. So if you see a demo and the demo's done with JavaScript, it's likely that the JavaScript is like ancient. Okay? It works only because we haven't broken anything in the years. Everything in Box2D is done with floating point values. So just expect that, which means if you need like a pixel coordinate for something, you're going to have to turn a floating point value into a truncated integer. The magic behind that is math.float, or floor, rather. The math floor function is very, very fast performance-wise, and the parse int function, which is part of the window object, is very, very slow. Right? So that's just something that people empirically tested and tested and tested. Went, wow, math.floor is about 100 times faster than parse int. So if you give math.floor a string like 100px, which you might take out of the CSS, it'll return 100. Really slick, right? There are other cute ways to do it in JavaScript. You know, you can multiply something times 1, but multiplying it by 1.0 doesn't make any difference in JavaScript. It's not like it magically turns it into a flow. Okay. Yeah, there would be math. So be prepared. Most of the math is on the rendering side because the physics engine handles the collisions. You will need values like pi. You will need possibly to use radians as opposed to degrees, although you can kind of do this in degrees. You may need a sine and a cosine to figure some stuff out. You may not. You will need vectors. All forces are vectors. Right? Floating point, arbitrary length vectors. So when it comes to Box 2D, there's only one world. You only create it once. You got to hang on to it once you create it. So that's why I say when we talk about architecture for our application, it's that middle controller layer that we're building. Build a world object. Have the world object have a couple properties like view and model. In fact, that's a nice consistent way I've done most of mine. I have a view property and a model property for every controller. The view property is a jQuery object hanging onto the specific thing in the DOM that this thing controls. And the model one hangs onto a Box 2D thing. Now it's relatively easy when I tell the world to do something that the world can go ask its model or its view. Everything in Box 2D works on MKS units, which is meters, kilograms, and seconds, which is going to be our first bone of contention, because what does set interval work on? Milliseconds. So everything in the physics library works on seconds, not milliseconds. So 16 milliseconds, if you were to set an interval, would be 0.016 in Box 2D. So you got to do that math yourself. Not really hard, you just have to be aware of it. There's a couple other things, and for Nick's sake, we're going to flip to this guy and make it. It's on here. Let me know when you've got the teams worked out, David, and then I'll stop and we'll kind of sort out.
I'm still missing James' message and I'm missing Dave's message. Dave's message out.
So, yeah, when we start talking about Box 2D, is that in the next part? Right. We're going to start getting this. So, Box 2D's world. That's just totally normal, right?
Yeah.
Is that the way the web works?
Not
Right? So when we talk about those two coordinate systems, the camera's kind of too far away to really see that board very well. Recognize that they have slightly different origins and slightly different orientations. I mention it now, it will trip somebody, probably many people, up. Why are my things not going? Why are my things flying off the screen? Well, because you think they're starting here and going that way. And in fact, they're starting here and going that way off the screen. Or you think they're starting here and going up. Of course, up is immediately off the screen and you don't see it. So just be aware they have different coordinate systems. In terms of scale, we also want to scale things. Because the physics library works in meters, we don't want to make our game so that 1 pixel is 1 meter in scale in the physics world, because we're going to end up asking the physics engine to do an infinitely small amount of calculations to move something in a really small area. So I typically scale it at 20 to 1 or 30 to 1. Right? 20 or 30 pixels per meter kind of thing. Just a scale factor to multiply by. Yeah, 20 to 1. Everything again is floating point numbers, so you're going to have to coordinate those two things. You can see from the slides here the difference in the coordinates. Oh, I didn't mention this part. Box 2D's origin's in the middle of the screen. And your screen coordinates are different, right? So that means you're going to have to do some math when you place something in the world. If it's pixels left, right, x, y, ends up being here, you got to translate it to this coordinate system. So you got to do the translation yourself. So whoever is doing the import, load, all the data, creating all the game objects to begin with, is going to build a game object controller. That game object controller is going to be created out of the data you load from your level loader. So the level loader loads data, you parse it, it turns into an array of JavaScript objects. It'd be really cool if my game object took one of those objects as a parameter and created a box 2D thing and created a div on the screen, and they were like in the right spot with each other. Right. This is our same main event loop. So once you build the world, then you start building a whole bunch of game objects. Those game objects all have a model part. You register the models with the world's model, and you can then let the world go. So you draw it by walking through all the game objects and ask them to render themselves. And then you're going to update the simulation by telling the world to simulate a little bit of time. And then you're going to walk through all your game objects, and they all have a reference to their model, part in the rigid body in box 2D. And you're going to ask them, hey, where are you now? Right. And from that, you're going to render where those things are. So here's some snippets of code showing you how to put some of these pieces together. These aren't all stitched together, and these aren't complete. These are the hard parts, if you will, the parts that you may or may not figure out on your own. All rigid bodies live inside a world. So we start by loading the physics library. This is really just a JavaScript object, and every property in there is a method, and the method remaps the box 2D. I'll pop it up for you. I'm going to give it to you.
Okay.
Right? Use it. It's easier. I'm defining a constant called gravity, which I've already used. I've already defined it, physics.gravity. I've got a vector, and I'm going to create a vector 2 for a 2D vector, starting with 0 and gravity, so x, y. So we go back to that coordinate system, right? Negative y. Right? Now, the next thing I'm going to do is I'm going to create a world using that vector. And this is our world model. This is not our world controller. if you find the terminology confusing, use the full names. Call it a world controller and a world model. I typically call them the world. That's my controller. And my world has a model property and a view property. And the view property is a jQuery thing, and the model property is that thing. So my world controller will do all of this work. All right. Now, the basic building blocks for putting together Box 2D entities is this weird construct they have. You can define a definition object. So that body definition creates you not a rigid body, but the definition for how to create a rigid body. And then you can set some parameters on that rigid body. And at the very end, you tell the world to create a rigid body with your definition. And the reason they do this is so that you can create multiple rigid bodies with the same definition in a nice looping structure. Right? So if I had to create 100 balls, they'd all be the same.
So basically, when I start loading the lab, it's going to got all the collidables, all the targets, it's going to create one gate object with all the information that I have into the JSON file and create like those things in Box 2D.
Right. So just like when you load a level right now and you walk through all the collidables, and for each collidable you create a div on the screen.
Yeah.
Okay. Well, now you're going to do some additional work. You're going to create a div on the screen, but you're also going to create a rigid body. Okay. Which means you kind of want to build a game object, and it'd be really cool if that game object's constructor took the exact JavaScript object you got from your level data, right? Because then you could go grab entity element 0, create a new game object with that element 0, and it would do all this internally. Does your brain hurt?
Not so much.
Okay. As well as having a rigid body, you also need a shape. Okay? Like I said, rectangles, circles, triangles are all cool. They work really, really well. I suggest staying to rectangles as much as possible because they work really nicely. You can build polygons. In all physics cases, stay away from concave hulls. Okay? And the reason is more game-centric than anything else. And if I'm going to try this a little bit closer and angled so that you guys might actually see it here. Not quite. Not doing very well with that. Okay, so I was trying to get this on, right? So our concave hull, right? That's the concave part, right? Okay, take a step back. Anyone ever played a third-person action-adventure game?
Probably. Yeah.
Probably?
Yeah.
Okay. Have you ever gotten that action-adventure game and you're walking along the edge of the mountain? Top-down look, right? You're walking along the edge of the mountain and you walk into the wall, what happens? You bounce out, right? It's pretty normal. If you walk into a wall, you bounce off a little bit. What happens if I draw this a little different? What if I zoom in and instead of drawing my convex hull, you know, my mountain here, what if I draw it like this? Really narrow. Okay. What happens?
Okay.
It gets worse.
Yeah.
So as I come off here, typical physics, angle of incidence is angle of reflection. So I'm going to get bounced out that way. And if I'm a good programmer, I'm going to bounce you off the wall a little bit because I don't want you dragging along the wall the whole time. So I drag you off to here, right? At which point you run into this wall and hopefully you bounce out. Now, depending on how big I made that bounce, when I do it here, now you're partway through the wall, right?
Go to the force.
And when I bounce you out,
You're out.
for all my Skyrim fans,
That's a feature for feature.
that's not a programming problem. That's a world builder, level builder problem. Hey, level builder, why are you building levels that people get bounced out of? Don't make concave hulls. Convex hulls are fine, because you're always going to bounce away from them. Okay? Where this interacts when we're playing with Box 2D and we're playing with 2D physics is I can have a very small thing right here, and when it hits this at any force, it's going to get shot that way. And it might bounce inside that, and then all sorts of bad things happen. And usually my simulation's broken at that point. Okay. So the easiest way to avoid that is use the rectangles and circles that are provided by Box 2D. Okay. Now, Box 2D allows you to rearrange these things. This is kind of the picture you should have in your brain of the way the Box 2D model hangs together. I create a rigid body that has a density, okay? Or rather, the density goes in the fixture. So I create a rigid body, that's the center of mass. That's where the center of mass is going to be computed. That's also what collides with other things. I've got a shape, and that kind of takes up some physical area in my model. And I've got a fixture that ties the shape to a rigid body. So I'm going to build up this structure. It more often is this linear structure. So for every element that you bring in from your level editor, you've got to build a rigid body, a fixture, and a shape for, as well as the DOM thing that you were building before. And you have to keep track of all of this, because when the world updates, it updates the rigid bodies. And when it's time to re-render all of your game objects, you have to walk through your list of game objects, extract their rigid bodies, extract the information from them about where they are in the world and what rotation they currently have, and then update your CSS to match. Okay. We talked about impulses and forces before. It's just down here. How are we doing, David? We close?
Yeah.
Right. It's almost time to put in another ticket for this room overheating.
Oh yeah, it's kind of
For the seams to the best. Don't feel the balance.
Sure. That's fine. Okay.
Double check one
So-
thing. Nick just answered, but
Yep.
I think it's fine.
To do that, and we'll write them up on the board, and then we'll take a short break where we'll give you your teams. You got to come up with a name for your project, because we're going to name the repo in our GitHub repo PG22 _ project name. Right? Probably call it PG22 AP _ project name. And then each one of you will clone it. It'll be empty. Each one of you will clone it here. And then you'll have to decide which level editor to use, and you'll make a copy of your level editor. Copy all the files over. Now there's some structural stuff we got to do as well when we go to do that. So we're going to take a short, just 2-minute break here while I flip over and go grab some code to show you some structural stuff we got to take care of. There you go. I got to do it 3 times, so you're going to get to see some of them. So here's Angry Football. I'm just going to copy that now. And grab a new one, clone it, put that there. I'm going to browse to my destination path. New folder, Angry Football. And clone it. Then I'm going to go grab the same set of files I had before. And I'm going to take all of those files, I'm going to commit them. Come on. Oh. Put them in the right folder. They're uncommitted changes, so I'll stage them all. Commit.
Oh, it's not.
Yeah.
Clone it and set git lfs install required.
Yes.
Should I say okay?
Yes. Say yes.
Okay, say yes.
Commit those. Push those. Cool. Now we'll do one more. That guy. Just remember the first clone has to be in an empty folder. We got some uncommitted stuff. Stage those. And push it all. Okay, a couple other things typically we'll do. We got to get a folder structure that kind of works here. And I said you're going to pull one of your level editors. What I want you to do is pull it into a subfolder. Okay, now you can copy it with the node modules and all, but that's kind of wasteful. So what we're going to kind of do here is do a little bit of massaging around of files and folders to give us a better kind of project that we can work in. And in order to do that, we kind of got to look at the way we're going to set this up. So the first thing is I typically use Visual Studio Code, and Visual Studio Code has what they call a workspace. And that's a Visual Studio Code thing. And that workspace gives Visual Studio Code, it says here's the root folder and everything else in this project is below that. So I can throw that in there as well. Now, I would rename it. So in this case, it's going to be and it's got the extension .code workspace. When we use Visual Studio Code to pop this up, and I'm just going to go here now. Typically, I'll open Visual Studio Code and I'll open a folder. So you can see here I've got the whole demo folder open. And here's the Cowboys versus Aliens one that I just did, and you'll see the different files. Well, with this code workspace, you'll see it's incredibly complex. And they're always the same, no matter what project. So you can just copy them all over the place. But it also, it pops up this code workspace button at the bottom. And when I click on that code workspace button, now I just have this project and nothing else. So I can switch workspaces here by just opening a new workspace. You can,
you show it
yeah.
again. Can you show it again?
So if I go back here and just go open folder, I open my demo folder, right? So here's all the folders in my demo folder. Right? Now, the reason it's important with Visual Studio Code is if you want to do anything custom, like use Visual Studio Code's debugger or integrated Git tools, you need to be working in a workspace. So when I do Cowboys and Aliens, I click on the code workspace and it pops up this button in the bottom right. And you can open the workspace. Ta-da! Right? So once you have one of them, which I'll drop in using Git, you can use Git to pull them locally. Okay. Now I have this. Now, what I'm not going to do for you and put into Git, this recognizes that it's a Git repository now. You can tell that. It's right here. That's what this little icon is. This shows me changes. And I can push, pull, commit from here. Integrated development environment. So I don't have to go out to source tree. I just do it from here. If you want to get fancy, I have a fancy plugin that I actually use. Not Git Lens. This guy here, called Git Graph. This is just a plugin. You can install it if you want, but Git Graph shows you a Git style graph and gives you right-click menus on everything. So I can go here and go, you know, clean all the untracked open source control view. I can stage, and I can go grab the repository and go commit all the staged files. And I can sync those changes with GitHub. Doesn't that make it easier to push things as you go? Hey, I want to get what everyone else has done. I can go here and go pull all the latest changes. Okay? So it's kind of cool. Now, you want to work on something, but you're not sure it's going to work? Git has a really nice functionality for that. It's called a branch. And there's a couple tools and workflows that people have defined, and they're just ways of using branches. The common way of setting this up is to come here and initialize what we call Git flow. It'll call it master. You have to change that to main. But the way Git flow is supposed to work is when you start working on a new feature, you go to the Git flow button and you say start new feature. And it creates a branch called feature / and whatever the feature name you gave it. And when you finish a feature, it automatically merges the develop branch into your feature branch, and then your feature branch back into develop. And if that's a little confusing, you don't have to use it. The whole idea when we start talking about different source control parts is that from a working perspective, oh, this is going to work. This is a long way away. From a working perspective, on a really shiny board, I have a main branch. That's typically what you guys are working on. And in the real world, that's what we release to the public. At some point, I start working on a feature. So I fork a new branch, I call it develop. And I fork another branch for every feature. Okay? As I make multiple commits to the feature, I get it working. And when I get it working, someone else may have modified this develop branch. So before I do anything, I have to merge the develop branch back into mine, which creates a new version with all the merged code. It's all on my machine and it's all in that feature branch. I make it work again because somebody inevitably checked something into the source control system that broke my stuff. It was never my fault. It was always someone else's stuff breaking mine. Okay? Just make sure you're clear on that. And then when I finish the feature, it merges it back into develop. And I keep going. Feature B. Okay, now Git flow supports this mechanism. When the build manager or the source control people come along and say, hey, it's time to make a release for client XYZ, they merge this way into that main branch. And quite often they'll tag it, label it, or branch it, release 1.0. And this will keep going this way. So that's a 20-second overview into source control and version control. But the big part of this whole process is it scales. It scales from 2 people to 200. Right? So you learn the techniques here with 2 people, where you can yell across the room to them, hey, you didn't commit your stuff, I can't work. Right? And you get used to the workflow, and that way when you get into a company that has 150 developers working at the same time, and they can commit 10,000 things in a day, you have an idea what to do. So you can initialize Git flow and use it, or you can just manually create those branches. But typically, the one thing we would do is, if we're more than 2 people, we would initialize Git flow. And it just makes life a little bit easier for you. And just like that, there's a plugin for that for Visual Studio Code too. So you can do it all from Visual Studio Code. I click the little feature button or bug fix. I click the feature button, it's got to play, create a new feature, stop, finish the feature. Right? And it'll automatically create the right branches for you. So they're just kind of like shortcuts to doing this manually. I'm going to do this manually. Okay? The idea in your head is main is always working. Always, always, always working. Right? So you can commit stuff locally, but you never push stuff that's not working. Because you don't want to like break all the other people on your project. The next part we'll do here, I'm going to create a new branch. So I'm going to create a new branch called develop. And I'm going to publish it. And it doesn't look any different. What this tells you here is the highlighted or the bold one is the one you're currently on. If it's got the keyword origin behind it, that's a fancy keyword to say this is on GitHub too. So it's also known as main. If it hasn't changed from main, they'll be the same. Right? And then the head revision, or the most current revision. And when you make changes there, you can see them here as well. If I just refresh this with an F5, I can see that's all there. I can also see all my branches here. And the one that's highlighted is the one I'm currently in. Okay? So what I recommend you guys do with two people projects is create a develop branch to work in. And keep your mindset that main is working. So if you get to a good place where develop kind of works, you could merge main into develop, then go into main and merge develop into main. You always merge something into the branch you're currently in. Okay? And then you go back into develop again and keep working. Okay? And you'll have multiple people checking stuff into develop, that's okay. It only becomes second nature if you use it all day, every day. Once you use it all day, every day, and the first time it saves your ass, you will never go back. Right? We've all done it, myself included. Cleaning up my machine, grabbed a folder, deleted it, emptied the recycle bin because I've been doing it all afternoon. Clean, 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 empty recycle, clean, 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 empty recycle. Oh shit, there was something in there I shouldn't have deleted. Right? And the first time you do that, and then you go back and you just clone it again, you're like, whew, didn't lose anything. And once you do that once, you're like, that's it. Everything goes in here now. It's my safekeeping. Okay, structure-wise, we can now just work in the folder. And what I'm going to suggest you do, you don't have to do it exactly this way, but you're going to have a node project. So you're going to have node modules. And that's not something that ends up in source control, but you do have to make sure that the project, or the JSON file, what's it called? Package.json file ends up there. So when you copy your level editor over, I would copy it into an editor or a level editor folder inside this folder. Okay?
Inside the main folder, another folder called level editor.
Yeah, and then we're going to mess with it. Okay? Because what we're going to do is we're going to pull bits out of it into the root of the folder. I don't want to duplicate node modules. That's my big thing. So when I start thinking about how this is going to work, I'm going to set it up so it's kind of structured like this. Now this is a file explorer too, so I can create new folders here. But I'm going to have a node modules folder. That'll be the one I'll pull out of my level editor. Okay. If you want to do it nice and clean, you can do an npm init, that'll give you a new package. You can do that right away if you want. The next thing I'm going to have here is an editor folder or a level editor folder. That'll be your level editor. Okay. I'm also going to have a game folder. And it's possible, if it makes sense, a common folder. Because there may be bits that I use in both. So I might have common CSS. I might have common JavaScript objects that I want to reuse. There's no point writing them twice or making copies of them. Copy's evil, right? That means when you make a mistake in one, you got to go find all the other places you made it. Now, because our application starts from server, I put the server in the root. my server. Okay. And as soon as you start doing this, you'll recognize that we have to do some work here. Like this goes to an editor folder because it goes and looks in the subfolder called editor. So I might have to augment some paths when I massage things around to get it to work. As far as this common and game folder, leave them 100% empty until your level editor works in this structure. Okay, get the level editor back up and working. So in terms of things to do, finish the level editor tonight. Make sure it's in your Git repo. Update your README. This is the link to my Git repo. This is the branch I want you to pull. Right? If you want to make a release branch, that's fine. And here's the command I want you to run my editor. npm run whatever.
Yeah,
Right?
on how to use, yeah.
And then how to use it
Yeah.
if I need instructions. Yeah.
Yeah, and right, we'll do it and run and open the browser and go localhost.
Yeah.
6
So put all of that stuff
to the README file.
in the Git repo, including the README file.
Okay.
Take the README file from the Git repo, put it in Moodle.
Yeah.
Right? Just same file.
Yeah, same.
Don't write a separate file.
Yeah, sorry for that.
Just use the same file.
Oh, the same README should be in it.
The same README. See, the way GitHub sets this stuff up, is whenever you go to a repository, it interprets the README file. So for instance, in Empress Eternal, it finally opens up, they have a README file. Here's the README file, and here's what they wrote in it, in their markdown format. Here's the high concept of the game. Here's our key features. Here's the links to our game design and our technical design. Here's the controls for the game. What's in what scene, all their debug tools, and who worked on what. That's a nice README. Now, if you wanted to go look at that and clone the readme.md file and use it in your team project next term, that would be really good. People would appreciate that. We will ask you to do it specifically for your final projects as well. But if you get used to writing these READMEs, this is what you put into Moodle, is that README file. That's it. That's all you need. Then I know where to go to get it. You got to add a couple things to this one, right? You got to add the URL. So, once you get that all set up, that's tonight's assignment submitted, right? Once it's into Moodle. And then make this folder work
To your final project.
for your Angry Pigs game, but make the level editor work in that folder by making a copy of it. Once it works in this folder, grab it all, stage, commit, push. Get on Discord, right? So typically that's going to fall on the shoulders of whoever's level editor you're using, because you're only going to pick one. Okay. I also have some other things that I recommend. I put the rest of my server stuff in the server folder. Okay. Particularly, I put my data in the server folder. You can put it in the root if you want, right here, because the server can see everything. Remember that you can't see any files higher up in the tree than where your server is. That's why I put the server at the root.
How should we choose whose level editor to use?
Bare knuckles.
I mean, like maybe, for example, somebody's level editor is like looks better, but another's has, for example, a different feature.
The game has no marks for the level editor. The level editor is a tool for you to use. So choose the one that makes your life easier building the game. my level editor doesn't just have one server and one index file. My level editor has a level object. It knows how to save and or how to parse a level from the DOM and how to take a level structure from the server and turn it into the DOM. Right? So I would want to reuse that as opposed to writing it again. So whoever's works better, choose that. You might need to actually run them both. But wait till you get tonight's assignment done before you do that.
Tonight's assignment being the love letter. Tonight's assignment being the love letter.
Is that what it is? I don't know. I don't pay attention to dates once I set them at the beginning of the term. Then you can put all of this together. We will show you some stuff with the server going forward to make it a little bit easier. In particular, this is kind of redundant, right? Because it's just grabbing an index file. This guy in particular is something I will show you guys in the future. So my API is buried underneath another file, and that file uses the Node Express router, and you can have as many of these here as you want. So each different API or portion of an API can drop in there. Now this API is really simple. It's really got 4 things in it, right? So it's not too crazy. Make sense?
So about the node modules, I have no modules on the level editor, right? I'm supposed to put them into
Yeah, I just drag the folder up
just that.
because everything's relative paths, so it'll just, right? You have an editor that has a server.js, and the node modules is at the same level as the server. So if you grab the server and node modules and package.json and package lock.json and pull them up to the root and leave anything else behind in the editor folder,
Should work.
should just work. Except that when server launches editor, like inside editor, you'll have index.html and main or index.js as the starting points. And those paths might need to make sure they're relative and they move. It's really just, you know, making sure your paths are truly relative.
So no modules are not going to the GitHub. How are we gonna use the server? How will the server run well?
So when we start this stuff, I'll just show you this one. So another version of the same thing. So the way the stuff works, so here's my server at the root, and I also have my server folder and node modules up at the root. So when I run this, this is the guy that's important, package.json. Package.json identifies all the dependencies, all the libraries I need, okay? It also identifies all the scripts I will run. So when I test the server, I do npm run server. It goes and finds this script called server, and it runs this command line. If I want to run just the client, you see I change directory into the game folder and then run the live server because it just runs.
But you didn't, for example, install Node.
No.
But how?
Oh, NodeMon's installed globally.
But when we installed it globally, it didn't work, and you said.
It needs to be in your path. Anything that's a tool, you'll install globally and make sure that your app data npm folder is in your path.
Because I already pushed everything to GitHub with no modules.
Yeah, so you just burned up a whole bunch of disk space that's obsolete already. And there's no way to get rid of it, ever. Okay, so don't do it again. Don't worry about it, but don't do it again. The reason is node modules gets big
Yeah, I know.
because it's got all the dependencies in it. And all of that code gets updated every time you update node. and or any of the packages. And you don't need any of it because this package.json is what you do need. Because this, if you go into this folder, like when I go get your stuff, I don't have your node modules, right? But if I have your package.json, if I go npm init, it'll go read package.json and install all the modules in your dependencies into my folder. Okay? Anything that's a tool that you want to run from the command line, you install globally. If it's not a tool like the cores module here or the ESM module or Express, it needs to be installed locally. And then you notice my editor, I have the index here underneath the editor folder. But in the common folder, I also have like the common CSS stuff. And then the index file in the editor here uses relative paths to find the, you can't see with the stupid thing. It uses the relative path to find the style base. Gotta go up one folder, and then down into common, and then down into CSS, and then you've got style base. So that way my editor and my game can use the same style base.
But CSS editor is not run.
This is relative to wherever this index file is.
Yes, but
Right.
do you have it?
I do have one.
Oh.
Do you get the way the file structure kind of helps?
I got the overall idea.
Okay, I do not have
We created.
It's not the only way to do it, and it's not, you know, it just reduces duplication.
Yeah.
That's all. You could technically have the editor in the editor folder with its own node modules, and the game in the game folder with its own node modules. But then, of course, as soon as you,
So I need just one server, right?
yep, and you'll run the server locally to test it. In other words, both of you run the server, right? Because you're going to create some data, right? This is why I've got the user ID in there. So I've got data files here. They are going into Git. So those do get saved in GitHub.
And then, yeah, you know that.
So if I build a level, my partner gets the level,
Yeah.
right? Wait till we get to complicated apps that have more files.
Not excited.
Keeping the file system straight is a matter of sanity. You will go insane. Now, can you imagine having multiple Angry Pigs folders? Right. So, recommend we definitely kind of do those things. Now, on the game side, right, we're going to start all over again. We'll build an index.html. I can tell you for a fact, when I built my index.html, I copied my editor's index.html into the game folder, and I just started ripping stuff out and removing it. Because I want the same basic game area, right? So I want to use the same styles. And this loads a local index.js just like the editor does. So you know, they both load index.js relative to where they are. So this is completely different. My game index is very different than my which one do I got?
Are we actually going to do some physics in the class?
You want to? Sure. You got 10 minutes?
No, I think next class will be.
Yeah.
One question.
Yeah.
So we're going to divide between what's your are the two main parts that you said to us to divide between us?
I would have one person, you can divide it any way you like,
Yeah,
really,
just-
but I would have one person take care of like the data side of things. In other words, building the physics model, loading data from the server, right? Building the initial DOM elements, that's fine.
And we show
And I would have the other person do all the render methods in the controllers and all the user interface, all the HTML and the CSS and the. It's time consuming, right? Just getting the thing.
Okay. One
Put
part
together.
for physics.
The other one for the rendering.
Yeah. Yeah. You will cross paths because you're going to be editing the same files at the same time. You know, to.
I can do HTML and
Here in the nation. Okay. So,
Let's do. Let's do this.
Have a short list here? No. We can set it up.
So let's just open my own Angry Pigs. Yay. I'm going to rename that so I don't get confused. Right? And now, as I get into here, I'm going to start to have to structure my game. So let's just do this. Right? And then I'll cheat a little. And then in main.js, that guy in. A little AI thing, try and take along, and then let's go. Do window. Just a main thing. Maybe it'll work. Right. Some people separate these out in separate files. And then in here, what am I going to need? I'm going to need constructor. And what do I got to put in my constructor? Well, or if you want to use JavaScript's private stuff, you can put that in there. And then I'm going to have update.
Why are you making private? No.
Right?
Why are you making private with double underscores?
Because when I look at it in the debugger, it looks like something the system created. Oh.
Why?
That way, when Jim looks at it, he'll think the browser created it and he won't touch it. Right?
Yeah.
But I don't want to tie this dot private, so I'm going to put a little shortcut there. You can do all sorts of crazy things with JavaScript. And then I'm going to have a run method.
What do you mean? What does it run? Like from the start?
Hmm?
As soon as you load the whole app, it's running.
Yeah.
Does updated render does it? Or it's just like from the start?
What do you mean?
Like on load of the app, like when you click like reload page, that runs.
Yep.
It doesn't run.
Doesn't do anything,
Yes.
right? But yeah, it runs.
No, I'm saying DOM elements are loaded from the first like load, or whenever we change.
DOM content loaded is an event that's thrown once the document is finished building.
Yes, but then it's like edited. It's being edited every time we're playing. So is it always being edited?
No. No, it's on first load.
Oh.
On first load from the server. Right? If you're worried about it, you can just run the risk that everything's loaded fast enough. This will run. Right? It just,
There's lots of-
this will run because this index is so small.
Yes, but
Right.
we will have like a lot of fetching first.
Yeah. Yes. And you can see here, I'm using them from the root, but this is the part where you'd have to like make them all relative. When you do like this, it says from the root of where the server's running. So, in this particular case, because common is right off the root, it could work. So what we'll do next time is we'll flesh out the details here and start building some of the physics things. Okay? So we'll incorporate the library, get that physics object working. I'll put the library in Moodle so that you can take a look at it.
It's just the question is, if we choose to make it in Unity, how many grades we're gonna lose?
If you choose to make it how?
In Unity.
If you choose to make it in Unity, you should be done in a day,
Yes.
right?
How much
But that's
grade?
because somebody else is doing all the hard work.
But it's gonna look like you expect, so we're gonna get some marks, right?
Yeah, I don't know that it would look any better. The real Angry Birds was built like this, with this library.
I think it was like an app.
Hmm?
It was an app for phone.
It was a progressive web app.
Really?
Yep. Just like this is a web app. This guy? This is HTML, right?
Wait, yes.
Yeah. Yeah. Yeah, the first Angry Birds was done as a web app, and you can make progressive web apps that can install to the desktop as applications. They can also be installed to the App Store. So basically it's a browser where you don't see any of the outside trim on it. And that's the way they deployed it, so they could get Apple, Android, and the PC without having to write the code 3 times. And they did use this library, right? Which means you'll have a ton of respect for them after you use this library. It works. It's just it's got its own idiosyncrasies.
Okay, is physics here as hard as in Unity if you don't use physics, if you don't like use rigid bodies? Is it like
No, it's about the same. The difference, the real difference, especially from my experience, is anything you're doing in 2D, whether you do it here in Unity, it's pretty much the same work. If you're using a library to do the math, right? When you progress to 3D, life on the web gets insanely difficult because you have to do all of your own rendering on top of that.
Are we gonna do 3D?
No, not in the web. It's not worth it. Right? So that's kind of one of the.
Have you done it?
I have, but it's painful. Right? Yeah, I'll demo it at some point. And you still have to use some libraries to do like WebGL, but yeah, as soon as you're doing 3D, that's kind of the place where the game engines just do so much of a better job faster that I wouldn't use the web to do it. Yeah. Let me just shut this down. Okay. And we're